All right, let's move on and let's discuss the relationship between pressure, temperature, and volume. Okay, so we've already taken a look at what pressure and temperature and volume mean, and now we're going to look at the relationship between these three. And we will begin with Boyle's law. And Boyle's law is a gas law describing the inverse relationship between the pressure and the volume of a gas at constant temperature. Right? I actually brought this up in a previous video. I said, well, what's going to happen to the volume of a gas if you increase the pressure? Right? Think about a tennis ball. If you squeeze it, if you increase the pressure, what's going to happen is the volume is going to go down. And so we see that pressure and volume are inversely proportional. And so what that means is if I take pressure and I multiply it by volume, I'm going to end up with a constant. I'll just call that K. And so that means if we take an initial pressure and we multiply it by an initial volume, it's going to be equal to our final pressure multiplied by our final volume because this constant K is not going to change. And so you can see that demonstrated here with the diaphragm and how it controls the volume of the chest cavity. So now that we've covered Boyle's law, let's take a look at Charles' law. And Charles' law is a gas law describing the direct relationship between volume and temperature. Right, this makes sense. I talked about it in the previous video. What's going to happen to the volume of a gas if you increase the temperature of that gas? Well, think about it. If you have an aerosol can that's practically empty, there's only gas in there. You put it in a fire, what's going to happen? The volume's going to go up. It's going to explode. Okay, so volume is directly proportional to temperature. Or we could say volume divided by temperature gives you a constant K. And so we can rewrite that formula like this. We can say initial volume over initial temperature is going to be equal to final volume over final temperature. That's Charles' law. So you see right here, this is exactly the example I was talking to you about. You have a gas here that has a certain volume and it has a certain initial temperature. Well, what happens after you jack up the temperature? What's going to happen? It's going to take up more space, right? The volume is going to increase, and that is Charles' law. So again, Boyle's law is the relationship between pressure and volume, and Charles' law is the relationship between volume and temperature. The next law is a combination of both Boyle's law and Charles' law called the combined gas law, a gas law that describes the pressure, volume, and temperature behavior of a gas sample when the amount of gas is held constant, where Ti is the initial temperature, Vi is the initial volume, Pi is the initial pressure, and the ones with F are all the finals. Now, something I neglected to point out in the previous slide, and I'm actually going to scroll back there, is that when you're using Charles' law, any gas law, temperature, maybe I'll just circle it here. I'll say temperature must be in Kelvin. If it's not in Kelvin, the law won't work. Also, when you're doing the combined gas law, the temperature, where is it? Right here. Temperature must be expressed in kelvins. If it's not in kelvins, okay, it will not work. So when you're using Boyle's law, Charles' law, or the combined gas law, forget about degrees Celsius. Only Kelvin is going to work. So with that in mind, let's take a look at this example here. Example 6.4, carbon dioxide gas is used to fill the abdominal cavity to create enough space for the surgeon to see and operate during laparoscopic surgery. A sample of carbon dioxide is known to have a volume of 5.00 liters. So volume is equal to 5.00 liters at a temperature equal to 25 degrees Celsius and a pressure equal to 0.951 atmospheres. What will what volume will the sample have if the temperature and pressure are changed to 50 degrees Celsius and 1.41 atmospheres? So notice that these initial conditions that I described, these are all initial, okay? This is where we started. And then what the question is saying is we're changing the temperature. The temperature final is going to be 50 degrees Celsius, and the pressure final is going to be equal to 1.41 atmospheres. And so I've pasted that all at the top. So what are we missing? We are missing the final volume, right? That's what they're asking is what will the volume of the sample be? So what we're looking for is final volume. So we're going to use our formula. We're going to use the combined gas law. which is P initial times V initial divided by T initial, is going to be equal to P final times V final minus, or sorry, divided by T final, like this, okay? And we're going to be solving for the final volume. And so to solve for final volume, we're going to say final volume is going to be equal to the initial pressure times the initial volume times the final temperature divided by the initial temperature, initial temperature times the final pressure. Now, if you're wondering, how did I get from here to here? This is algebra, okay? And if you remember at the beginning of the class, I mentioned you have to be able to solve an algebraic equation. And so now that we have that set up, we notice there's one other problem, isn't there? Is that the temperatures are not provided in Kelvin, are they? They're provided in degrees Celsius. So we need to convert both of those into Kelvin. So we're going to add 273 to both of those. I'm going to just do this in my head. So the initial temperature in Kelvin is going to be 273 plus 25, which gives us 298 Kelvin. The final temperature is going to be 273 plus 50, which gives us 323 Kelvin like this. And now we're ready to do the math. So we're going to say our initial pressure is 0. Maybe I'll use my black pen. Is 0.95 atmospheres. Our initial volume is 5.00 liters. Our final temperature is 323 Kelvin. Our initial temperature is 298 Kelvin, and our final pressure is 1.41 atmospheres. And you can see that now that I've set it up correctly, you see the atmospheres cancel, as do Kelvin, and we're left over with the units of liters, which is good because we're looking for a volume. So when you take your calculator and you punch all of this in, what you're going to end up with for your final volume is going to be 3.66 liters as your final answer. All right, and that brings us to the ideal gas law. And before we get into the ideal gas law in detail, let's discuss Avogadro's law. Avogadro's law is actually my favorite of all the gas laws. And it tells you that, and you have to think about it very carefully. Okay, Avogadro's law, I would say, is it's my favorite, but it's not actually intuitive. Check this out. It says equal volumes of gases measured at the same temperature and pressure contain equal numbers of molecules. Now, when you first read that, you might think, okay, big deal. Like, what's the deal? Okay, no big deal there. If I have equal volumes of gases, same temperature, same pressure, equal number of molecules. Good. Yep. Well, hold on. What if we're comparing two gases that have very different masses? What if you're comparing H2 gas, which has a molar mass of about 2.02 grams per mole, versus something like CO2 gas, which has a molar mass of about 44 grams per mole? Okay, so that means that CO2 is like 20 times heavier than hydrogen. And so what they're telling you is that if you have two balloons, here's one with H2 gas, and you have another one here that's equal size, roughly. I'm trying to draw equal size. I'm not a very good artist. CO2 gas is that these are at the same temperature and at the same pressure, and they have the same number of molecules. So it's again, it's not that intuitive because carbon dioxide molecules are bigger than H2 molecules, right? But remember what I said is that we treat gases like they almost don't take up any space whatsoever. It's like their sizes are negligible. And so what that means is that the volume is going to be directly proportional to the number of moles of gas, irrespective of the identity of the gas. Okay. So we can write that and we could say, well, volume divided by the number of moles is going to be equal to some kind of constant, which won't change. And so we can rewrite Avogadro's law, as you see here, initial volume over initial number of moles is equal to final volume over final number of moles, like that. Next, let's talk about standard temperature and pressure. And standard conditions, what we call STP, standard temperature and pressure, is a set of specific temperature and pressure values that we use for gas measurements. Now, the standard temperature when we're doing gas calculations is actually 0 degrees Celsius. And you're like, well, what kind of laboratory are they doing reactions at 0 degrees Celsius? Wouldn't we choose room temperature, like 25 degrees Celsius? Maybe, but anyhow, that's what chemists have chosen. So standard temperature is 273. Kelvin or 0 degrees Celsius. But standard pressure is the pressure at sea level. Okay. So remember, 1 atmosphere is the atmospheric pressure at sea level. So if you're in Colorado like me, I don't live at standard pressure, do I? Right? I live at a pressure below this. But anyhow, and so a relationship that you should know is that if you have any gas, or sorry, 1 mole of any gas out of standard temperature and pressure. So if we have 1 mole of gas at 1 atmosphere and 0 degrees Celsius, it's always going to have a volume of 22.4 liters. Now, if you're wondering how big is 22.4 liters, you can see that they have this beach ball or something here that has a volume of 22.4 liters next to this 1 quart of vinegar. Anyhow, it's kind of like bigger than a basketball, is what I would say. If you take a basketball and, if you were to take that and make it bigger, anyhow, you can't see my hands, can you? But anyhow, so that is a volume you need to know. So again, repeating myself, if you have 1 mole of any gas, doesn't matter what it is, it's standard pressure, standard temperature, it always takes up 22.4 liters, always. And so, with that knowledge, that if you have 1 mole of gas at 1 atmosphere and 0 degrees Celsius or 200 273 Kelvin, always has a volume of 22.4 liters. With that in mind, we come up with something called the ideal gas law, which is a law that relates pressure, volume, and temperature and number of moles in a gas sample. And so we say pressure times volume is equal to N number of moles times big R times T, temperature in Kelvin. Now you're probably looking at this and going, what the heck is R? Well, the R is known as the universal gas constant, okay? And we can actually solve for R. You can see here, they put in standard pressure, standard temperature, 1 mole of gas always takes up 22.4 liters, and we get this number 0.0821. Check out these units, liters times atmospheres divided by moles times Kelvin. And so again, this number is a constant, okay? It's this R right here, and it is a constant that we are going to use. So make sure you memorize the universal gas constant. All right, let's take a look at this problem. Nitrous oxide, N2O, is an inhaled gas that is used as a pain medication during childbirth. Use the ideal gas law. So we're going to use PV is equal to nRT to calculate the volume of 0.41 moles of nitrous oxide gas at a temperature of 20 degrees Celsius and a pressure of 1.20 times 10 to the power of 3 torr. Well, remember that R is equal to 0.0821 liters times atmospheres divided by moles times Kelvin. And notice that they've given us 0.41 moles. That's no problem, okay? That's our N. We know the gas constant, okay? And we're trying to solve for volume, but they've given us pressure in torrs, and we need to convert that into atmospheres. And so let's do that first. We know that our pressure is going to be equal to 1.20 times 10 to the power of 3 torricelli. And we know that we have 760 torrs in, eh, in 1 atmosphere. Let me try to make a neater line here. 1 atmosphere. So we see that torrs cancel out, and we end up with 1.58 atmospheres. Next, they've given us the temperature as 20 degrees Celsius, but we need the temperature in Kelvin. So I'm just going to add 273. So our temperature, I'll just scribble it. I'll just scribble it right here. Temperature is actually going to be equal to 293 Kelvin. So 293 Kelvin, 273 plus 20. That's just a calculation I did in my head. And so now if we take PV is equal to nRT and I solve for volume, I get volume is equal to N times R times T divided by P, like that. So now I can just plug in my numbers. So let me get a little bit thinner pencil here. So I get 1 point, no, 0.41 moles times R, which is 0.0821 liters times atmospheres, divided by moles times Kelvin, multiplied by the temperature, 293 Kelvin, divided by the pressure, 1.58 atmospheres. And look at this. It's not magic. Check this out. Look, moles and moles cancel. Atmospheres and atmospheres cancel. Kelvin and Kelvin cancel. And I'm left over with what? I'm left over with liters, the unit I am looking for. And so when I punch all this into my calculator, I get my volume is equal to 6.2 liters. And there you have it. Remember, this law, PV is equal to nRT, this is the ideal gas law. But just quickly, an ideal gas actually doesn't exist. It's an approximation that we can use for most of the temperatures and pressures that we're going to be interested in studying gases under. But it says here the ideal gas law is presented in equations 6.2 to 6.6 of Boyle's law, Charles' law, combined gas law, ideal gas law only apply to gases that are ideal, but no ideal gases actually exist. Now, before you get stressed out, in this class, we're only going to be worrying about ideal gases. Okay, so it's an assumption we're going to make. However, you should be aware that real gases deviate from the behavior that's predicted by the gas laws, but under, again, the normally encountered temperature and pressures, the deviations are so small, and the ideal gas laws can be used to predict the behavior of real gases. Okay, so don't stress about any deviations from the laws that I taught you in this chapter. This is kind of an FYI. The reason why a gas wouldn't behave ideally is because of intermolecular forces, right? One of the postulates we had at the beginning of the first video in this chapter was that the gas particles don't interact with each other, they're not attracted by each other, they're not repelled by each other. But we know as a consequence of intermolecular forces, that's not true. We know that gases are actually attracted to each other a little bit because of London forces, even for nonpolar gases. And if you take gases that are polar, like water vapor or HCl, which is a gas, or ammonia, these are going to deviate significantly from ideal behavior. Why? Because they have permanent dipoles or hydrogen bonding. So they're going to be even more attracted to each other than molecules like O2 and N2, which only have London forces. But again, and I'm repeating myself for probably the third or fourth time in this slide, don't worry about deviations from ideal gases in terms of calculations, but just know that an ideal gas technically doesn't exist. We're going to use these approximations, these laws, for anything that we're going to talk about. But because of intermolecular forces, gases actually can deviate from ideal gas behavior. But again, we're not going to worry about it a whole lot in this class. All right, let's talk about one last gas law, and this is Dalton's law. Sometimes it's referred to as Dalton's law of partial pressures. And first of all, we need to define what a partial pressure is. It's the pressure an individual gas, the pressure an individual gas of a mixture would exert if it were in the container by itself at the same temperature as the mixture. Okay, now that might seem a little bit complicated, but it's what leads us to Dalton's law of partial pressures, which is the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the gases in the mixture. So all that means is if you have a bunch of gases mixed together, the total pressure of the mixture is going to be equal to the sum of each one of the individual gases together. So let's take a look. Let's say you have these three containers here. You have the triangle gas, the circle gas, and the square gas. Okay, these different gases, you can see how they all have different pressures. Okay, well, if you were to take all three of these and put them in here, okay, to make a mixture, the total pressure here is just going to be the sum of this one, and this one. And if you're like, that's it, Dalton's law is just total pressure is equal to the pressure of, the first gas plus the pressure of the second gas plus the pressure of the third gas, so on and so forth, which is what you see right here. That's all it is. That is the law, okay? And if you're thinking, man, all I have to do is just add these pressures together. Yep, that's it. Students usually love Dalton's law. So let's take a look at a question that involves Dalton's law of partial pressures. So the question is, nitrox is a mixture made of nitrogen and oxygen that's used as a breathing gas in pressurized tanks for scuba divers. Hyperoxia, caused by an excess of oxygen in tissues, occurs when divers breathe in oxygen at a partial pressure greater than 1.6 atmospheres. At a dive depth of 99 feet below sea level, the partial pressure of nitrogen in a nitrox mix is 2.72 atmospheres, and the total pressure exerted on the diver by the combined atmosphere and the water is 4 atmospheres. Solve for the partial pressure of oxygen at this depth as the diver exceeded the oxygen partial pressure limit that can lead to hyperoxia. Well, remember that Dalton's law states that the total pressure is going to be equal to the pressure of the oxygen plus the pressure of the nitrogen. Now they've given us the total pressure. So total pressure, maybe I could just move this down here. Okay, they've given us the total pressure and they told us that it was 4 point, come on, pen. They told us that it was 4, come on, 4.00 atmospheres. And they told us what the pressure of the nitrogen was. So I'm just going to leave PO2 in here because that's what we're looking for. The pressure of the nitrogen is 2.72 atmospheres. To solve for the pressure of oxygen, we just say 4.00 atmospheres, subtract 2.72 atmospheres, and we get the pressure of our oxygen is going to be equal to 1.28 atmospheres. And so the pressure of oxygen at this depth does not exceed the safety limit of 1.6 atmospheres. And so here's a summary of all the gas laws that we studied. So Boyle's law, it deals with pressure and volume. So pressure is inversely proportional to volume, Boyle's law. So P1 V1 is equal to P2 V2, or P initial times volume initial is equal to P final minus volume initial. I just like 1 and 2 versus initial and final. The next one, Charles' law, which is volume is directly proportional to temperature. And so VI over TI is equal to VF over TF. Then we have the combined gas law, which is really just a combination of both Boyle's law and Charles' law. Then we discussed Avogadro's law, which tells us that volume is proportional to the number of moles of whatever gas we're studying. So VI over NI is equal to VF over NF. Then we have Dalton's law of partial pressures, which we just looked at. The total pressure is equal to the sum of the partial pressures of all the individual gases. And then finally, the ideal gas law. PV is equal to nRT. Remember, R is equal to 0.0821 liters times atmospheres divided by moles times Kelvin. And so it's imperative that when you're doing Charles' law or combined gas law or the ideal gas law, that the temperature is always in Kelvin whenever you're dealing with gases.